Which one? No. Can I go backward? Yes, I can. Okay.
Now change the slide.
Which one's wrong?
Yes, now I can.
Okay, good. Hi everyone, welcome to this session of the summer class. Today we have Jakub Czerkowski presenting MIMDRAM paper, which was originally presented in HPCA 2025. Yes,
Yeah.
something like that. This is a very interesting work bridging the gap into adoption of processing-using-DRAM. And the interesting thing is that Geraldo, who was the first author of this work, presented his PhD defense final presentation yesterday, and he has also a lot of other interesting works in the direction of processing-using-DRAM or near DRAM. So I also, additional to this paper, invite you to check those works if you're interested in this direction. So yeah. Now we can present.
Okay, thank you. So hello, my name is Kuba or Jakub, and today I want to present to you MIMDRAM, which is an end-to-end processing using DRAM system for high throughput, energy efficient, and programmer transparent, multiple instruction, multiple data computing. That's a mouthful. Okay, so let's start with an executive summary of the paper. So the problem is that existing processing using DRAM architectures suffered from DRAM's large and rigid granularity, and that causes that the SIMD substrate to be underutilized, and we cannot take advantage of the parallelization available. We are only limited to perform mapping operations and cannot perform reduction operations, and it's rather difficult to program. So the goal is to design a flexible PUD system that can exploit parallelism at smaller scales, allows for in-DRAM data movement to support reduction operations, and lastly provides a software infrastructure to ease adoption. So MIMDRAM is a hardware software co-designed PUD system that enables finer grained computation down from row size to just 512 elements. It adds cheap interconnect to support data reductions within DRAM. It allows for multiple instruction, multiple data execution just within DRAM, and provides compiler and OS level support to improve programmer experience. And the key results include the significantly better energy efficiency compared to state-of-the-art PUD systems, along that better than high-end CPUs or GPUs. And all that comes at a rather small area cost of about 1% to the DRAM chip and the CPU die. So let me first give you some background. So as we all know, the computation has become more and more memory bound in the recent years. Even as much as 60% of the total energy, system energy, is spent only on the data movement. So to address this, a lot of people have proposed multiple different processing in memory architectures. There are two main approaches that we differentiate. There is processing near memory, where we put the logic layer on the same die or close to the CPU or close to the memory. And there is processing using memory, which uses the operational principles of memory cells to perform computation. And MIMDRAM is the latter type. So some background on how DRAM is structured. First, we start with cells, which are organized in 2D grids of which we call mats. We have a local row decoder, which connects to the rows using the word line. And then we have the bit line, which connects, which allows for transferring data from the rows to the local sense amplifier. Then zooming out, we organize our mats in a subarray. That's we put the multiple mats next to each other, and together they form a DRAM row. We also have a global row decoder that drives all the local, connects the global word line to the local mats. And we have the global sense amplifier that forwards the signal from the local sense amplifiers to the I/O interface from which it can communicate the data to the CPU. So as some brief, how exactly does this DRAM row access happen? Is that we first send a precharge command, which prepares the sense amplifiers to read the data. Afterwards, we send an activate command to the row that we want to read the data from, and in turn, that causes the sense amplifiers to sense the current variations in the cells, and that's how we can read out the value contained within cells. To actually perform computations in DRAM, we have to first know how to use the substrate. So first thing we will need is a in DRAM row copy. That is, we will copy one row in DRAM to another one. And we can do that by performing back-to-back activations to different DRAM rows. What happens is that when we first prepare the sense amplifiers, they're ready to sense the data. We activate the first row, the data gets sensed, and then we activate another row, and then what it makes it happen that the data gets fed back into the destination row too. Another component that we'll need is in DRAM majority operation, and this can be achieved by activating 3 different rows in DRAM simultaneously. And what will happen is that the sense amplifier will choose the majority of the 3 operands, which is a 0 or a 1. Together, these we can orchestrate these in DRAM row copies and majority operations to implement different circuits. For example, here we have a simple circuit that performs additions, and we can transform that to use only majority operations. And that's how we can actually perform meaningful computation inside of DRAM. It's important to mention that the operands are not stored in the row anymore, rather in a column. That means normally the data is stored next to each other in the same row, whereas now we will store the data within columns instead. Okay, so let me now discuss what are the problems that today's PUD systems face. So there are 3 main problems, and they all stem from the same root cause, which is the large and rigid granularity of DRAM. And the first problem is that we underutilize the available parallelism that DRAM provides us, which leads to throughput and energy waste. So we first will define a vectorization factor, which is how parallel a computation is. So for example, if you look here, this blue row, it doesn't use the whole DRAM row, which means that we cannot utilize the full parallelism of that the DRAM just accessing this whole DRAM row would provide. In the paper, the authors performed an application analysis to quantify available parallelism across and also within a single application, and we can see that majority of the applications parallelism is significant is below the row size, which is about 65,000 currently. And there's in some application, the available parallelism also varies just within that application. And this is the problem. So another problem is that we have very limited computation support. We're currently only restricted to perform mapping operations. So for example, given an array of numbers, we cannot collect the numbers and compute its sum, because the data is, we don't have any substrate to move the data between different columns. So if we were to add a direct connection between all DRAM columns within a subarray, that would lead, unfortunately, to significant area cost. So we won't be doing that. And last, the programming model of how to program a DRAM chip to perform useful computation is rather complex and problematic. So given this relatively simple loop that basically does conditioned addition or subtraction, this would translate roughly to this equivalent bulk binary operation code. And what the programmer is responsible for is for mapping and aligning the data, because we need to make sure that the data is row aligned. we need to identify array boundaries such that we can change the loop into these operations. We need to unroll the loop by hand, and we have to convert those addition to bulk binary operation add, for example, here. And lastly, we need to arrange for data movement, which is like we have those extra arrays here, that the E and F that were not present in the previous one. And this is rather cumbersome, error prone, and we will prefer that to be done automatically. So to this end, we propose the authors of the paper propose MIMDRAM. And the key idea here is to leverage this finer grained granularity for PUD computation. And there are several key ideas here. First one is that we only allocate the appropriate computation resource as to avoid underutilization and have less energy waste. The second idea would be to concurrently execute multiple independent operations in different DRAM mats, that is to increase throughput. And lastly, we'll want to implement a low-cost interconnect to transfer the data between DRAM mats and DRAM and columns within a single mat, with avoiding any CPU intervention. So let's start with the first one. We'll segment the word line. So there already exists a finer granularity than a DRAM row, and these are namely mats. So we reduce the granularity from about 65,000 to just 500. So the observation, we can just use the global word line, but can use the global word line, but also only access parts of the DRAM subarray. Then how to achieve the second idea is that we can observe that within the segmented word line, we can selectively interact with only a subset of the DRAM mats. And this will enable us the execution of different commands between different independent DRAM mats. And that will allow, in turn, for multiple instruction, multiple data execution model. And lastly, to implement a low-cost interconnect, we'll observe that first, there is already some interconnect that will allow us to transfer the data within a single DRAM mat, as well as there is already some interconnect that will allow us for transferring data across different mats. And yeah, we'll only perform minimal changes to enable that. So to summarize, MIMDRAM is a hardware-software co-design that enables finer-grained PUD computation at lower programming effort and low cost. And yeah, first now let me give you an example of how this intermat data reduction can be performed. So we want to perform a computation that is C equals A plus B, and we have 10 one-bit numbers spread over 2 DRAM mats. What we first do is compute the C1 and C0, which are the two parts of this reduction, which is the sum of those one-bit numbers. Afterwards, we can perform an intermat data movement, as in to bring the C0 part into the mat 1, And finally, we can perform the final reduction of C1 plus our temporary, which was the C0 row, C0 mat row. Now let me go over what hardware changes we need to do to enable all of this. So to enable segmenting the global word line, we'll add isolation transistors and row decoder latches, as long as alongside it mat selector that will allow us to selectively choose a subset or a sub-range of mats that we will want to operate on. To allow for inter-mat data movement, we'll add a really lightweight layer of multiplexers. So these are basically 2-to-1 multiplexers that allow us to move the data from a neighboring mat to another one. And to enable moving the data within a single mat, we'll employ the help of the helper flip-flops, which are already available. And we'll do that by kind of violating how the operational principles of how they are normally used to move some data across different columns. Finally, to orchestrate all this operation, we'll need a control unit. This consists of a bulk binary operation buffer, which stores the instructions given to the system by the CPU. Which then we have the math scheduler that will choose an instruction that can be executed by consulting the math scoreboard, which gives us the information which matrices are currently available for usage, which maths are currently available for usage. And once we find a suitable instruction in our binary bulk operation buffer, we'll schedule this instruction to one of the microprogram processing engines, which will in turn start performing the execution. So now let me now go over the software component of MIMDRAM. So we'll start with the some compiler support. And our goal is to automatically extract SIMD parallelism from source code and schedule PUD instructions to maximize SIMDRAM parallelism utilization. And we'll use, the paper uses existing LVM compiler infrastructure to implement 3 different classes, which I'll briefly discuss now. So we start with SIMD identification. So that means we look at the LVM intermediate representation and look for instructions that can be performed in parallel. We choose an appropriate vectorization factor that will give us the best throughput. And finally, we can also get rid of the data movement, since all the data now is resident in RAM, so there's no point in moving the data from memory to the CPU. The second step is to perform code scheduling and data mapping. So we construct the data dependency graph, which is this picture here. And it allows us to see the dependent operations and schedule them. And it's scheduled in the fashion we also need to map the operations to DRAM maths, similar in the fashion to how a CPU has to perform register mapping. And finally, what we need to do is generate the final binary by allocating the data and inserting appropriate bulk binary operation instructions. Now let me briefly mention the system software, the system support. This includes the instruction set architecture that includes operations such as additions, multiplications, gated like if-else statements. We also MIMDRAM also gives us an execution and data transposition support. As I previously mentioned, we have to transpose the data from the row format to the column format. We have to take care of data coherence, because we need more system use caches, and we need to make sure that we don't work against them. Finally, we need to perform address translations from virtual to physical addresses, and perform data allocations, alignment, math label translation. And I will not go into more detail of these out of brevity. So when it comes to the evaluation, the MIMDRAM was compared to CPU, GPU, the previous work of the group, which is SIMDRAM, which is a PUD system, as well as DRISA, and also a processing near DRAM system, which is Fulcrum. The researchers performed a 2-level analysis. First, they started with a single application, that is to measure how much intra-application parallelism the MIMDRAM can extract. And then that follows the multi-programmed workload analysis, which highlights how much inter-application parallelization can be achieved. So starting with single application workloads, MIMDRAM significantly improves energy efficiency, especially compared to the CPU, GPU, or the previous work of SIMDRAM by 37 and 14x respectively. When it comes to multi-program workloads, even in the most optimistic case for SIMDRAM, where it uses bank level parallelism, MIMDRAM is still 1.68 times more efficient in terms of throughput. And lastly, comparing MIMDRAM to other team architectures, MIMDRAM has significantly better performance per area compared to DRISA by about 1.18%, 1.18x, and about 1.92x compared to Fulcrum. Other results include that the with subarray and bank level parallelism, its MIMDRAM is significantly more performant than the CPU and the GPU. It achieves comparable throughput to the other PIM architectures, and has, which was the main goal, it significantly improves the SIMD utilization compared to the previous work. And all that comes at a rather small area overhead of about 1% to both DRAM chip and the CPU die. And there are, of course, there's more thorough analysis in the paper. So now let me conclude. So to sum up, MIMDRAM is a hardware-software co-designed PUD system that enables finer grade computation at low cost and easier programmability. The key idea was to leverage finer grained DRAM for processing using DRAM operations. And in hardware, we made simple changes to allow MIMD execution and added a low-cost interconnect to allow data in DRAM data reductions. And from the software side, we added compiler support and OS level compiler and OS level support to reduce the burden on the programmer. And yeah, we achieved significantly. The MIMDRAM achieves better performance, energy efficiency, and throughput compared to state-of-the-art PUD architecture, as well as CPUs and GPUs, and all that at a rather small area cost. Okay, finally, let me now go over some strengths that I have found in the paper. So first one is that I really appreciated that MIMDRAM is really aimed at driving the processing using memory towards wider adoption. They want to allow make it easier for programmers to shift into this paradigm of programming, even transparently, so that the programmer doesn't have to know. It's aimed towards more intelligent memory. So that means that the more and more logic is offloaded of the CPU die. It only includes minor hardware changes and simplifies the workflow for a programmer to make processing using DRAM system work. And finally, following the fact that it uses LLVM as its compiler support, this also makes this rather language agnostic, because a lot of other languages than C or C++ can compile down to LLVM. And there are unfortunately some weaknesses that I have identified as well. So I'll start with the rather unified code identification and generation strategies. So what MIMDRAM does is it optimizes solely for throughput. So that means that whenever an instruction or a loop can be mapped to a PUD operation, it will do that. And it does not consider a cost model. So basically, it has a rather simple cost model. So the cost model is, I see an instruction that can be mapped to PUD computation, I map it to a PUD computation. And this is partially, the paper mentions it, why that's the case, and it's mostly attributed to LVM being not generic enough to support the variable SIMD width of MIMDRAM. The second issue I have identified is that the performance within multiplication or like more complex operation dominated workloads is worse than in a CPU or a GPU. That is caused by the fact that multiplication uses quadratic number of operations, because we need to, for example, an addition would only use a linear number of operations, because we need to simulate the whole adding circuit of n binary digits. Whereas for multiplication, as you know, like you perform multiplication on paper, it usually requires about quadratic number of steps. And the issue is that we cannot, since the goal of PUD computations is to improve throughput, we cannot always hide this high latency of the multiplication computation if it's not available. Then, while MIMDRAM adds a lot of flexibility, there are still some things that we cannot do. So the first thing is we cannot perform floating point arithmetic. the benchmarks that the researchers have run, they translated the floating point arithmetic to fixed point numbers. And another thing is that the global in DRAM data movement is still rather limited, and that also limits how we can do the data mapping inside DRAM, because it's limited only to the neighboring mat, and is, as far as I understood it, is unidirectional. So we can only move the data from the left matrix to the from the left mat to the right mat. Yeah, and that is a source of unoptimized code scheduling and data mapping. So first of all, this code scheduling is, again, insensitive to the operation type. So for example, it will schedule the code the same way if we perform additions or we perform multiplications. And it follows a very relatively simple approach by just recursively following the leftmost path and mapping it to the same mat, and then recursively doing that for all the unmapped subtrees. But overall, I think that PUD is an really important research avenue, especially in the context of energy efficient systems, because the biggest advantage is that we achieved significantly better energy efficiency compared to the PUD, to the CPU or a GPU, just because we avoided a lot of data movement. The second takeaway I would say is that there are two different fronts that can drive the PUD adoption. So that first one is that we don't necessarily want to perform drastic hardware changes, because that will be an issue for the manufacturers to implement, and all the committees to convince that this is indeed what we want to implement. And the other is that we want to make it easier for the programmers to program these systems, for example, by hiding this fact pretty much completely by doing this automatically. And lastly, this paper highlights how we need to optimize across the entire software hardware stack in order to implement new ideas that have potential to change the principles of how we compute. Okay, so that was the the paper part, and now I want to pose you some questions. So my first question to you is, given that MIMDRAM PUD generates PUD code with the goal of solely maximizing SIMD throughput, given sufficient vectorization factor, it always maps to PUD instructions, right? So what do you think we could also is this even the most optimal way to optimize code? What do you think? Or do you think that what would happen if a program is compute dominated? Is mapping always to PUD instructions always good? Can you come up with a scenario when it's not good?
Well, I have a question. Is it if you don't have a big vector or anything, you just want to do like two very simple a simple operation, is it always slower to use the CPU?
So
you have to get the data and everything, but
yes. So the question is whether it's always slower to use the CPU. Well, that depends. Again, that depends on how many things you want to perform at once.
Yeah.
So given that, first of all, we cannot use the system if the vectorization factor is, for example, smaller than the single mat, right? But then still, it's not necessarily always faster to perform all the computations within DRAM. Given, like, for example, we've seen multiplication takes order of n² operations, whereas the CPU has that accelerated with some smarter hardware. So yeah, as I said, some PUD operations are really multiplication heavy and have bad latency. And my question is to you: what other metrics we can optimize for? What ideas do you have other than just pure throughput? Yeah.
Some quality of service metric. I don't have any in mind,
service,
but
okay,
yeah.
so like fairness and stuff like that. Okay, yeah, thank you.
Energy efficiency.
Energy efficiency.
Because in the end, if it's too energy inefficient, you can just clock up the CPU and do it on the CPU in the end.
Anything else? So we have throughput, fairness, quality of service, energy efficiency. Any other ideas? So we can also just strictly optimize for performance. So we can, as you said, mentioned already, it's not always worth to move the data to keep with the PUD computation model if we care for strict performance, right? That it may be more efficient to more performant or faster to move the data to the CPU, perform the computation and move the data back to the DRAM still this way. So yes, energy efficiency you already mentioned, and fairness, quality of service. Okay, so now given these, how can we optimize? Because we've already seen that MIMDRAM always maps to an PUD instructions, and this is because they don't employ any comprehensive cost model. So the paper mentioned that LVM IR is not expressive enough to represent the variable SIMD vector width. Do you have any ideas of how we can enable this more diverse, more precise optimizations? How can we? What can be done if we cannot use LLVM IR to represent those? What can we do instead? Yes.
Maybe use another compiler.
Okay.
Probably you have to change a lot, assuming I think MIMDRAM already implemented the framework, right? So you have to modify the entire framework to build on top of CLang.
Okay, so you can implement like a custom compiler, right? Yeah, that is perfectly possible. Any other ideas? Yep.
Manually annotate your code with some directives.
Okay, so we can manually, yeah. Okay.
Do you want to say it again?
Okay, yeah, we can manually, we can do this whole process manually. Yes, that is a way, but yeah, that of course then removes we go back to the previous kind of state where we were already doing this manually. So yeah, so what are the alternatives? Yes, we already mentioned creating a new custom compiler, and we deemed that rather impractical. Another way is to maybe we take what LLVM already gives us and then just tweak it a bit so that it works. But my suggestion that what we could use is opt for a more flexible compiler infrastructure. I don't know how many of you have heard of MLIR. How many? Can we do a show of hands? Okay, 1, 2, 3. Okay, 4 people. So what is MLIR? It's a newer compiler framework. This stands for multiple level intermediate representation. And it allows to represent target specific operations, such as, for example, PUD operations. So what we can do is translate only MLIR allows for a kind of mixed kind of instruction format. So we can mix in LLVM IR inside with some this PUD kind of domain specific language. And that then allows us to perform more generic optimizations that are already, for example, available in this framework. Yeah, and it's already, so we can basically define a more finer cost models that will allow us then to optimize for different objectives. Yeah, so as I said, we can implement this PUD instructions as like a domain specific language that then we can interleave with the instructions, with the normal LVM instructions, and then define a more interesting cost model that will allow us to optimize for different goals. Okay, my next discussion point is how is CPU and PUD computation different in the principle? So we already know that the CPU performs computation using bit parallel arithmetic. So it's, for example, the addition doesn't take O of n time, it rather takes logarithmic or / constant time. It's accelerated. So we achieve low latency. So from the things you have heard already, what happens for, So yeah, the operand bit size is usually constrained by hardware. It's usually 64 bits. Whereas with PUD, all operations are executed in bit serial fashion. So This means that additions take O of n time and multiplications take O of n squared time. And it's optimized for throughput rather than latency. So my question to you is, how can we potentially improve? What can be done to make this computation, this bit serial computation faster, since it seems that it's limited by the O of n and O of n squared. What can we do instead? How can we improve the latency of bit serial computation? So my hint to you is maybe, what are the maybe inputs that we can do we always need to compute on fixed bit width? Does that spark something in your heads? For example, given that we have numbers, we know, for example, that our data set only contains numbers from 0 to 10, and we'll be adding pairs of those numbers. Do we need, what can we do, and what would be different from the CPU model? Yes?
Encode or map the data differently depending on the workload?
Okay, so you mean, for example, we can decide that our numbers fit within a smaller bit width?
Yeah. Let's say if you can fit one number in 8 bits, you can pack 3 or 4 of these 8 bits into a 2 bit, and yeah, this would be the encoding.
Okay, so what we can do instead of using like a fixed size of 64 bits, we can be kind of more data aware. And what we gain is that our addition no longer and multiplication no longer take 64 squared or 64 operations, but rather however long our operands are, right? So this is already one paper, the paper from the same authors already partially suggest these. So we want to reduce the bit precision for some of the PUD operations by allowing for narrower bit sizes. For example, for 10-bit multiplication, we only need to perform around 100 operations instead of around 16 squared operations. So what advantages can you think of? What disadvantages can you think of allowing for variable width precision? Like, for example, what happens to the data layout? What happens to like the benefits should be relatively straightforward. As a first, we make it faster, right? That's pretty obvious. But what else? Maybe think how the data is not like, assume we have some fixed size data stored by the CPU. For example, we have these 16-bit numbers, but we know that we'll only use the 10-bit numbers, right? So this allows us to potentially save some memory because we can map the data already to 10 bits, and we don't have to pay for the price of, for example, because normally we have to have byte aligned accesses, but this allows us to skip that, right? So these are like the potential advantages of this solution. So faster execution and potentially smaller memory usage. What do you think that the disadvantages would be? Yes?
There's some complexity involved in implementing this, I assume.
Yes, so that's exactly it. So as you remember, or maybe not remember, so I'll remind you, we have this, we have to transpose the data from bit parallel format, so row format, to this column format. So then that would make this logic, this hardware part, this part potentially more complex. So that's one thing. Any other ideas for what are the potential disadvantages here? Okay, so I'll spoil it to you. The PUD program, microprogram generation might be more complex because before we had what was happening, we had a fixed kind of instruction set. Now we have to, for example, we had like additions of 32-bit numbers. Now we'll have to support the bit width as part of this instruction microprogram generation instruction that maybe might have been not clear. Yeah. And my next question is, what can we do if we simply cannot accept or hide this latency of bit serial computation? So we know that given that we have that our data is, for example, it's for 32 bits, it would fit exactly correctly, but that's still too slow for us. What can we do? Can you maybe think of some hybrid approaches? Also, maybe what if we want to support floating point arithmetic? How would we do that? And my suggestion is that we don't necessarily need to compute everything using DRAM. What can we do? Yeah.
Well, we can just use CPUs or the CPU to perform floating point arithmetic or latency sensitive applications.
Yeah, that's perfectly valid. So we will use some type of hybrid execution that will, for example, mix PUD execution and CPU GPU execution. For example, since PUD doesn't support floating point, we will offload that work to the CPU. Can we think of a more memory-centric way of doing it? Yeah. So what we can add is processing near memory components, right? So exactly, that's correct. So we can add kind of accelerators for the operations that we really care. So for example, we can add accelerators for floating point arithmetic and for the slow operations of, yep.
Wouldn't it kill the purpose of the entire year if you were to send half the program, half the question, half the execution?
Well, that's the big problem of how can we actually make good use of it, right? So,
yeah.
So
I feel like at that point, you guys just send the entire execution of the CPU.
Well, that again depends. How do we know it would be faster? Maybe if it would be faster, we might as well do it. If it won't, like if we optimize for performance, might as well do it. If we optimize for energy efficiency, still might be better to keep it in DRAM. So yeah, it's rather difficult to kind of know how to best use, how to leverage this. It's a lot of research has been put into it, and it's a really complex topic of how to eventually map these parts of computation to different components. And my last talking point would be how we can facilitate PUD adoption with SMD that we've heard actually a couple of weeks ago. So you can recall that SMD enables asynchronous in DRAM maintenance mechanisms, and that SIMDRAM operates at subarray granularity, while MIMDRAM uses MATS, which is one level lower. So how would you envision these two systems to work together, or what potential issues would you see? Any ideas? Yeah.
Well, if you rely on the DRAM to do calculations, then any locking to do maintenance operations could potentially increase the time it takes to actually compute.
Well, we already know that the maintenance operations have to be done one way or another. It's the question whether it's done by the DRAM itself or scheduled by the memory controller. So that technically shouldn't be an issue, because the maintenance operations have to be performed one way or another. So what would happen, for example, if we made SMD work at DRAM mat granularity instead? Do you think that will be good, bad, slow, fast, energy efficient, energy inefficient? What's your opinion here? So the question is rather, do we pay too much for making SMD this granular, right? Is that going to be an issue? Any opinions? It's more of an open question without a definite answer.
Question.
Yeah.
What do you think
On the durability.
Do you think it would change anything, or do you think it would be slightly less?
So whether it would the computation would affect the DRAM durability, I mean, I don't know how to answer that exactly. But what I can say is that DRAM durability has not been an issue so far as a memory substrate. It's more of an issue with NAND memory, right? There, the memory actually degrades over time. Whereas in DRAM, that has not been an issue. But I cannot comment really.
Fair.
If it would be a problem, my guess is not much, because we just perform the usual operations that DRAM would perform either way, maybe a bit more often, because these are just row activations and the row and pre-charging the sense amplifiers. Do you think that in what way do you think that maybe SMD could make the MIMDRAM faster? Is there an avenue that you can see that would happen?
I suppose then you'd have a lot of the maintenance to be dealt with itself within the DRAM, and you could have a lot of computation and maintenance be dealt completely in memory and not have to have the CPU have any overhead on it.
Yes, that's
probably
one
slightly, yeah.
One way.
Say so.
Yeah, what we can also do is we can kind of we have this. If you recall, we have this math scoreboard, which basically denotes whether a math is busy with computation or not. We can maybe leverage that to also note down which maths are actually used for computation. Maybe we don't have to refresh the rows that are not used for computation. Given that, like, since we already have this scoreboard, might as well use it for more kind of DRAM management operations as well. So, for example, we can map we can collect the information which maths are actually containing operation like data, application data. Okay. So it's like integration, like OS level integration.
Yeah.
Anything else? So if not, that will be it for me. So yeah, I presented to you MIMDRAM, this long text, and thank you a lot for listening to me.
Do you want to say something?
Yeah, thanks for the presentation. Just a few points to add. So as you have seen, processing using DRAM or processing near DRAM can provide a lot of performance benefits. So it's a paradigm shift from the processor-centric mode of computing that we conventionally have been using. So to enable the adoption of this paradigm and facilitate it, there are a lot of interesting research that can be done. There are a lot of problems that need to be solved. So Jacob presented some of them in the context of this paper, but there are still a lot more, as you can imagine, to be done. So if you're interested in these topics, feel free to talk with TAs in the course and people in the lab if you want to learn more or like be involved in solving some of these challenges. Yeah.
Maybe I'll comment one thing about DRAM reliability you ask. I think you were referring to RowHammer or kind of read disturbance. So actually we have an upcoming paper on ISCA so that we show that this put operations where you activate multiple rows at the same time. So if you recall that RowHammer is just you activate a single row at a time and then you sandwich a row basically. You activate the one aggressor and then you pre-charge, you activate another aggressor. And in between you have victim row. So here there might be a setting that maybe that's the rows that you're activating, maybe sandwiching a victim row. Basically, you're activating multiple rows at the same time, which sandwiches a victim row. So actually over there, we show that it's make things a lot worse, like more than, so we see that like 150x reduction in like the minimum time that you need to hammer. So that like empirically, yeah, and it is actually present not just for simultaneous activation of multiple rows to perform measures. It's when you do row clone even, you get let's say less hammer count to induce bit flips. Not necessarily row press. So row press is also different. So RowHammer. Yeah. So here in RowHammer, you keep the row open at minimum time, which is 36 nanoseconds, let's say. And row press, you keep the row open like longer, microseconds. But still, in both, let's say, attacks, you just activate only one row at that time. You keep one row open at a single time. So it's getting worse. And also another maybe aspect for not just put, but PIM. So there's actually another upcoming paper to DSN, which shows that this PIM operations, row clone and PNM, PIM-enabled instructions actually increases the throughput of memory side channels and covered channel attacks. I guess that one is already on archive. You can check for amplifying main memory, let's say, covered and side channel vulnerabilities. So yeah, there are a lot to be done in terms of both in the stack and also in the robustness and reliability of DRAM-based systems, I think. Yeah. That was all I want to say.